Okay, folks, hello again. So, we would like to start with this year's quantum mechanics course. As you will discover, there are many ways of doing quantum mechanics. Like, there are what are called perspectives. I could think of the Heisenberg, what's called the Heisenberg picture, and the Dirac picture. So the difference between these is this. In the Heisenberg picture, the state of a particle is specified by giving the probability amplitude that if you measure the position, you find the position to be x. So we actually use wave functions for this. When we use the Dirac picture, the wave function is given by a set of amplitudes that if we measure any observable, we have a certain probability of finding it. So we could represent a wave function as a set of amplitudes that if we measure the energies, we'll get energies E1, E2, and so on up to En. This being the probability amplitude that it will have an energy En. Or we could represent this in the momentum picture where the state is written as a linear combination of momentum states of definite momentum. Let's call this P1 plus B2, P2 plus, so in Bn, Pn, like that. So in the Dirac picture, it's not really important how we represent we don't really choose a particular way of writing our wave functions. We simply appreciate the fact that whatever representation you use, whether you use the representation in terms of eigenfunctions of the Hamiltonian operator, which is states of definite energy, or states of definite momentum, or states of definite position, what's really important is how you generally treat these wave functions, no matter what representation you use. Whereas when you're using the Heisenberg picture, we usually confine ourselves to position representation alone. I think I'm correct about this. I might be mistaken, but I think that's the issue. Now, in this particular course, we would like to explore the entire depth of quantum mechanics by making use mostly of the Dirac picture, because this broadens the scope of quantum mechanics, not just to make it a standalone discipline, but actually quantum mechanics becomes a tool that can be used to study a lot of other disciplines like atomic physics, nuclear physics, and quantum field theory and stuff like that. So the Dirac picture is a very important picture, and it's loosely based on the ideas of linear algebra. So you shall see the correspondence between the Dirac picture, which we shall utilize quite a lot, and linear algebra. Okay. Now, so the tools we're gonna gain are gonna give us more insight into a lot of branches of physics where quantum mechanics can be used as a mathematical tool for analyzing complex situations. Okay, but before we go further, let's talk about the notion of measurement in quantum mechanics. Okay. Now, whenever we are dealing with classical mechanics assumes that if we decide to measure the position of a particle at any particular time, we are certain to measure a particular value of the position. If likewise we also want to measure the momentum of a particle, we can find it as precisely. And knowing the momentum of a particle and its position, and guided by Newton's laws of physics, we can precisely predict the behavior of whatever particle we are dealing with. So classical mechanics has embedded in it certainty of measurements, certainty of measurement outcomes, and also determinism. So these are the underlying precepts of classical mechanics, and that's why it works so nicely. But you will be quite surprised that classical mechanics can be derived as an approximation for quantum mechanics. All the notions that we can describe with classical mechanics, they are really quantum in nature. It's just that we loosen some requirements and make some basic assumptions. I shall highlight that a little bit later. But then if we now talk about quantum mechanics, there's an intractable relationship between measurement and probability. Measurement and probability. So, if we have a state, say psi, that represents a particle, say in a quantum well, and we try to measure its energy, right? Oh, let's say we try to measure its position by using the so-called position operator. Now, so this is the position operator. It's acting on the wave function, which represents the state of the dynamic state of our particle. We are likely to get a set of possible positions the particle could have. So it could have the position x1, right? Or if we measure it again, we might find it to be at a position x2, or if we measure it again, we might find it to be at a position x3, and so on. So whenever we make measurements in quantum mechanics, we are usually not precisely sure about the outcome. We can never really quite predict the outcome of that measurement. All we can say is that if I make a position measurement on a particle in a quantum state, I'm likely to get a value P1 with a probability Px1. and the outcome of measurement could be x2 with the probability of measurement, with the probability of getting that x2 to be px2 and so on. So there is an inescapable relationship between measurement and probability. Like if you fired an atom, a silver atom, onto, say, a screen, every time you measure where it hits by observing scintillations on the screen, it will not hit the same place, even though each atom that's fired through this electric gun is prepared in an identical quantum state. But what it does is, at one point it might hit the center of the screen, at another point here, at another time here, there. So there's a possible set of outcomes that you can get from measurement, and each outcome has an associated probability of finding of getting that outcome of measurement. Of course, if our distribution is maybe concentrated towards the center, the probability of getting outcomes towards the center is higher compared to the probability of getting a position measurement outcome at the edge. So there's always a probability associated with quantum measurement. And the reason why probability enters into quantum mechanics is because of two reasons. The first reason is the uncertainty of the data. Like if you were to try to measure the position of an electron, like in this example where I was talking about a silver atom fired onto a screen, the data has an inherent probability distribution. It's never really precise. Instead of getting, for particles that are identically prepared and look exactly the same, they will not hit the same place but are kind of scattered. So there's an inherent uncertainty in the data that we record. Now, the source of this uncertainty in measurement is debatable. A lot of people debate where it comes from, but another important thing about how probability enters measurements is that whenever we make a measurement on a system, in quantum mechanics we usually talk about small mass systems or low mass systems. So low mass systems are usually less likely isolated, less likely to be completely isolated from the environment, from the surroundings. Compared to massive systems. Systems we see in classical mechanics. Okay, let me give you an example of this. Suppose you would like to measure the position of an electron. So you have an electron in a quantum well, and then this electron is traveling with a momentum p, or let's call it k, right? Which is the momentum. Now, if I try to measure position of this electron, I shall have to, there will be a lot of uncertainty in the position of the electron, because an electron is so small and it can be greatly affected by stray electromagnetic fields that surround our system. Like maybe if you make this a vacuum, but outside this vacuum and you try to isolate it as best as possible, there are particles like atoms that have charge, and the electric fields are always affecting our electron, and these electric fields are are, are behaving in a kind of random manner. So these are quivering electric fields, and hence their effect on the position of the electron is such that whenever we try to make a measurement, this electron will not be found to be in one place, but it's always quivering under the influence of the electric fields due to this matter that surrounds our cavity. Another thing is that the act of measurement itself can disturb a system. So in quantum mechanics, the act of measurement can disturb our system. Okay, how is that possible? Let me illustrate this. I think most of you have done first year optics. Let's say we have a microscope with a lens, and the lens has a diameter d. We have a source of light, and we would like to measure the position of an electron that is here. So the light travels like this and then gets refracted by the lens, and where the two light rays converge, that's where the position of the electron is. Or actually, the other way of saying is that the electron produces light which then is refracted by the lens of the microscope and then enters the eye of the observer. Maybe that's a slightly more accurate way of doing the measurement. And from optics, the uncertainty in the measurement of the position delta x is given by 1,22 lambda over d, right? This is kind of like I think it's called the Rayleigh resolution criteria or something like that. So in order to reduce the uncertainty in the position measurement of our electron, we have to use waves or photons of large wavelength. So we have to use photons of large wavelength. Now, if a photon is large wavelength, then its momentum P is given by h over lambda, right? Which we can write as h over 2 pi and then 2 pi over lambda. So this will be h bar times k. We call k the wave number. Okay. So for our am I doing this right? I'm not sure if I'm doing this correct. Let me see. Okay, so according to what's called the Heisenberg uncertainty principle, the uncertainty in position times the uncertainty in momentum, they should be greater or equal to h bar over 2. So if you require that the position be precise, you want delta x to be small, that means that the uncertainty in momentum is large, right? So which means that we possibly have to use photons with a large momentum to probe this electron, because the uncertainty in the momentum is large. And when we use photons with a large momentum to probe this electron, the result is that the momentum gets transferred to the electron, thus jogging it around and actually making the position more imprecise. Okay, I shall talk about the Heisenberg uncertainty a little bit later. For now, I'm just stating it as a result. Okay, another reason why there's an uncertainty in the position measurement is this. We have to make the diameter very large. So we have to choose a lens with a large diameter, like this. So if we're choosing a lens with a larger diameter for our microscope, that means that the path of the electrons coming from the electron, from the path of the photons coming from the electrons, has a large component perpendicular to the optical axis, and that large component perpendicular to the optical axis has an effect of disturbing the x position of our electron significantly, thus producing a large uncertainty in the position measurement. So this is kind of like a way of trying to maybe give you an experimental source of measurement uncertainties for position of small particles. So as a result of this measurement, whichever way we are trying to measure the position of the electron, it actually affects the position of the electron itself. Okay, but then we can, so in quantum mechanics unlike classical mechanics, we do accept that measurements are imprecise and involve disturbances. So measurements are imprecise and involve disturbances. Hence, we use probability as a tool to describe quantum system. But the way we use probability to describe quantum systems is unique only to quantum mechanics. I mean, there are many fields of study that might use probability, but the way we handle probability in quantum mechanics is unique only to quantum mechanics. Okay, so before we talk about real measurements, let's talk about what is the so-called ideal measurement. Okay. So let's take a quantum system represented by the generic state psi. We call this a ket, right? So this represents the quantum state of a system. So this represents the quantum state of a system. Remember, we say that for almost for all of these systems, quantum systems, whenever you make a measurement, the outcome of that measurement is uncertain. You cannot predict what you're gonna get as an outcome of that measurement. Okay. So if we take our generic state psi, right, and then we measure things like energy, momentum, or position, we know that the results are uncertain, right? So let's say we have our generic state, and then we measure energy. We measure the energy E using the energy operator. I'll talk about the operators a little bit later. Then we find that this system is in an energy state EI, represented by this ket, or this wave function. If we make a repeated measurement, since we now know that, we measured the energy first and we know we found the energy to be E1. If we make a second measurement of this state, we will be certain to find it in the state of energy E1. So like if we repeat measurement, we are certain to get a particular outcome, and this outcome we get it with a probability P EI. Similarly, if we have a generic state psi and then we make a momentum measurement, right, by applying the momentum operator, we'll find our state to be in a state, say, of definite momentum P1. If we make a repeated measurement of momentum, we will certainly find it to be in the state P1 again. And the probability of getting this outcome is, we'll just write it as P1. So any system, even though there is uncertainty in the outcomes of a measurement, from the results of an experiment of repeated measurements, we can generalize and say that any system has a quantum state in which the outcome of a measurement is certain. Of a measurement is certain. Meaning that, let's say if we have a state, generic state psi, there exists a state in which the outcome of measurement is, so let's say we have a state psi. So there exists a state, right? Let's call that state EI, in which the outcome of a measurement of energy is certain, and the outcome of that measurement will be EI. So in other words, this state EI, if I apply the energy operator to measure the energy, I'll be certain to get the energy EI and the state back. This is the so-called eigenvalue equation. I'm sure you remember something like this from linear algebra. But then the question is, these states where you are certain of the outcome of a particular measurement, they have to be special. Because remember, we say that when we make a measurement, we disturb our system and usually jog it into a new state. So there's something special about this state, of these states where you are certain to get a particular outcome of measurement, that ensures that they are not disturbed by the act of measurement. So, and this doesn't only apply to energy. We can call this states where the outcome of measurement of energy is certain to produce the energy EI. We can represent them with this cat. We can call the states where the outcome of measurement of position is certain to produce a position X, like this. Or we can talk about states where the outcome of a momentum measurement is certain to produce a momentum P. What we should know is this. So for the states EI, which are certain to produce a value of energy EI when you make a energy measurement, these are unaffected by energy measurement. A state X in which the outcome of a position measurement is certain to produce a position X, these are unaffected by position measurement. And a state P in which the outcome of measurement of momentum is certain are also unaffected by position measurement. However, what's important is this: the state EI in which you are certain to produce to measure energy EI, and the state X where you are certain to measure an outcome of position to be X, and the state P where you are certain to produce an outcome P for the measurement of momentum, are not the same. That is, they don't coincide. What does this mean? I mean, okay, maybe here these might coincide, but this and that do not coincide. What does it mean in quantum mechanics? That means that a particle can not have precise position, well-defined position and momentum at the same time. So particles cannot have well defined position and momentum. In the language of quantum mechanics, we say that the operator for x and p are non-commuting. This shall appear later when we start discussing operators in detail. So they are non-commuting we say x and p are non-commuting observables. So you can never simultaneously know the position of a particle and the momentum of the particle. Okay. Now, this might all seem very confusing. The notion of measurement in position and momentum and energy. So if we have the generic state psi that represents a quantum state, things like energy, position, and momentum are not properties that the particle actually has, intrinsic properties that the particles actually have. But these quantities represent questions that we can ask about the state through measurement. Right? So energy is not really something that a particle has intrinsically. We cannot say that this particle in this quantum state has energy. But it's a question that we ask, that if we measure this thing called energy, what do we get? Right? Do we get anything? If we measure this thing called position on this particle, do we get anything? So observables, it's kind of difficult to think of them as properties that the quantum particle has, but rather these are questions that we probe our quantum system by applying what the so-called operators. I know that it's a little bit confusing. The reason why I'm saying this outright at the beginning is so that we know how to speak the language of quantum mechanics without, because we have a certain language that we use when we speak of quantum mechanics, and I don't want you to get that language confused when you read papers and when you also write papers. The right language informs a better understanding of how these things work. Otherwise, if we have erroneous understanding of what these concepts mean, we might apply them wrongly and find things to be incredibly difficult. Okay, so I shall come back to the idea of observables and measurement, but for now, I think let me now talk about probability.